Okay, cool. Welcome to another tutorial. So in this tutorial, I want to derive the moment generating function of a standard normal distribution. Okay, so we know that the standard normal follows the mean 0 and 1, but we want to show it. So now we want to derive the moment generating function because once we have the moment generating function, so the moment generating function will give you moments. So one of the moments we get from the MGF is the expectation of x, which is equal to the mean of your distribution. So if it means if I get a moment iterating function for the standard normal, then I can use it to show that the mean, the first moment, is equal to this 0. Okay, so instead of memorizing this thing as zero, and also you can also find the second expectation or the second moment. So the second moment, this will allow you to find the variance. It's not equal to the variance, but it will give you the variance. Okay, so you can use it to find the variance, but it's not equal to the variance. So we start by finding the moment generating function from first principles. Okay, so we start with a random variable. X, and x follows the standard normal. Okay, so that means the density for this random variable, the density for random variable x, is just 1 over the square root of 2 pi times e to the negative 1 over 2x squared. Okay, and now this random variable has a support from negative infinity to positive infinity. Okay, so I want to find the moment generating function. So I say the moment generating function of the random variable x. So this is equal to, so this is defined as the expectation. It's the expectation of e to the tx. So it's e to the tx. So now this x is because my random variable is x, but if my random variable was y, then it was gonna be e to the ty. Okay. So it means I want to find this expectation of e to the tx. So the expectation is just gonna be the integral, because now we're dealing with the standard normal, it's a continuous distribution. So integrate from negative infinity, integrate over the support, so it's negative infinity to positive infinity. Okay, then you integrate, because now you want to find the expectation of e to the tx. So here you must have this e to the tx, then times your density function, this is f at x. Then you are integrating with respect to x, so the time variable is dx. Now we just need to plug in this density function. So you still have this e to the tx. Now you know your density function, just 1 over is this 1 over root 2 pi. So it's 1 over root 2 pi times e to the negative half x squared. So it's 1 over root 2 pi, 1 over the square root of 2 pi times e to the negative half x squared. Now you're integrating with respect to here, so you need to have your dx. Okay, so now here's what we have in this integral. You see that you have e to the tx, and then you have e to the negative half x squared. So now this e, so now e and e, these are just exponents. No, these are just bases. So e and this e, these are just bases. So once you have if you're multiplying same bases, you take one base and then you add the exponent. Just basic rules for exponent. Okay, so it means I have my integral from negative infinity to positive infinity for now. Okay, I will still have the constant 1 over root 2 pi. Then I would take 1e, then I add the exponent. So I will have e. Okay, so I'm adding these two exponents. So I'm adding tx and e to the negative half x squared. But I want to start with, okay, so when you're adding, it does not matter what time you start with. So I can start with negative half x squared, then I add the tx. So I just took one base, then I added the exponent. Then you have your dx. So what we have now inside this integral, okay, focusing on the exponent, you have negative half x squared plus tx. Okay, so we have this integral. You can solve this integral by any integration techniques, but now the easiest way to solve this integral is to say, okay, we have this integral. Remember, this integral is equal to the expectation of e to the tx. Found that is the integral from negative infinity to positive infinity, and then we 1 over root 2 pi e to the negative half x squared plus tx dx. Okay, so now looking at this exponent, okay, so you have negative half x squared plus tx, so you wanna complete a square. Okay, so you focus on the exponent, so you wanna take this exponent, then I want to complete a square. Okay, but I just only let this exponent equal to y before I complete a square, because now because now I have negative half x squared plus tx. I want to complete a square, so I don't know how to complete a square when I have a negative coefficient of x squared, and also if the coefficient is not 1. So I only know how to complete a square when the coefficient is not 1. So when the coefficient is 1, and also when it's positive. So this is the reason you set the exponent y is equal to negative half x squared plus tx. Okay, so now then we can remove the negative half, so by multiplying by negative 2. So you're just gonna multiply by negative 2 both sides. So you're gonna have negative 2y. Then you multiply by negative 2. Negative 2 and this negative half is gonna remove this negative half. It's gonna be positive 1. So now you're left with x squared. So but just remember the minus 2 will multiply all of the terms on the right hand side. It's gonna be minus 2 tx. So now once the coefficient of x squared is positive and also the coefficient is 1, I know how to complete a square. So I just complete a square on the right hand side. Complete a square, you open one bracket, then you put your variable x, then divide the coefficient of b. So this is a quadratic, so b is just negative 2t. You have to take the coefficient divided by 2. So you take negative 2t, we divide it by 2, it's gonna give us t. It will give us negative t, so you have inside the bracket you have x minus t. Okay, now it's gonna be square because now you're completing a square. But now remember that even when completing a square, this expression where you have completed a square must be equal to that expression where you have not completed a square. They must be equal, just that it's a different representation. Okay, so now if you expand x minus t all squared, if you expand this term, we get 3 terms. You get x squared minus 2tx, but you also get another term which is positive t squared. Okay, now you see that this term was not present in that original expression, so we need to minus it. Okay, so this is why we have to say, okay, after closing that bracket, you need to say, okay, you have the squared, you need to minus t squared, because if you expand x minus t all squared, you get 3 times, and you also get positive t squared, which you need to subtract to make sure that this left hand side is still equal to that left hand side above. Okay, now you still have your negative 2y. So now remember that our exponent is equal to y, not negative 2y. So you need to solve for y, just multiply by negative half. So you have negative half times, okay, negative half times x minus t all squared minus t squared. Just as it in negative half, so you're gonna have negative half x minus t all squared minus, so negative half times negative t squared is just positive half t squared. So now this is your exponent. So this part is this that's your exponent. So that's your exponent you had initial. So you need to put it back to your integral. So the expectation of e to the tx, the integral from negative infinity to positive infinity of 1 over root 2 pi times So we had this e to write exponent now, but now we've written our exponent as negative half times x minus t all squared plus positive half times t squared. Okay, so now remember what we did when we combine these two bases. We already exponent, but now we want to separate the exponent, which means we need to separate the bases. So this positive half must have its own base e. Okay, so now we're doing the opposite. Negative. Okay, we still have dx is equal with respect to x. You have 1 over root 2 pi. Now you wanna split these two exponents. You wanna split this exponent and this exponent. Okay, which means now you'll have two bases. So you have e to the negative half times x minus t all squared. Now I wanna have the separate base for half t squared. So I need to have another e. So I introduce a new base times e to the half t squared. So let's apply the laws of exponent to split the two bases. Okay, to split the exponents. Okay. Now, okay. So now the integral with respect to we're integrating with respect to x. That means anything which does not contain x is a constant. And now you have two constants. You have 1 over root 2 pi, which is a constant. Then you have e to the positive half. You have e to positive half t squared, which is also a constant. But now I want to move one of these constants out of the integral. So I will move this one. So I just take it out of the integral because it does not depend on x, and I'm integrating with respect to x. So let's take e to the half t squared. Let's take the e to the half t squared outside of the integral. So I have e to the half t squared out of the integral. Now my integral is there from negative infinity to positive infinity. So only times I have inside the integral is 1 over root 2 pi. So is 1 over root 2 pi, and this e to the negative half times x minus t all squared. So times e to the negative half times x minus t squared. And then you have dx to show you are integrating with respect to x. Okay, so now if you look at this integral, okay, so let's say if you look at this part excluding the dx, if you only focus on this part, you realize that this is a PDF of a normal distribution with a mean t. Okay, it's a PDF of a normal distribution with a mean t and the variance 1. So this part if this part is just it's a normal distribution with a mean t and the variance of 1. Okay, it's not a standard normal, it's a normal distribution. Now we are integrating a normal distribution from negative infinity to positive infinity. So like because this is a probability function, integrating over its support, this integral will just be equal to 1. Okay, because now you have e to the half t squared, and then we said this integral is just equal to 1 because you see that the part you're integrating is a normal distribution, and you're integrating the normal distribution over all the values it is defined on, which is negative infinity to positive infinity. So it's gonna give you 1. So now you have the e to the half t squared, which was just this part, which was a constant, times this 1, which you got when you're evaluating this integral. That gives you e to the half. So this will just give you e to the half t squared. So now remember that is e to the half t squared is the expectation of e to the tx. But now remember that in the beginning we said the expectation of e to the tx. Remember this part is the expectation of e to the tx is just the moment generating function of our random variable. So that means now we have found that this part is equal to the moment generating function of our random value. So the moment generating of a standard normal is just e to the half t squared. So that's what we are trying to prove. Okay, so this is what we are trying to prove. Okay, But now, okay, we have derived the moment iterating function, and in the beginning of this video I said that you want to use the moment iterating function to find the moment, to find the mean. So everyone knows that the standard normal distribution has got a mean. So this is our mean and this is the variance. So standard normal has a mean of 0 and 1. This is just a known fact, but let us try to use the moment iterating function to find these two these two values. So the moment iterating function of the standard normal is just, we've shown that it's e to the half t squared. So you have e to the half t squared. Now we're gonna use it to find the mean of the standard normal. Pretend you will know that the mean is 0. So here's what you want to do in this case. Okay. So you say the mean is just equal to the expectation, equal to the first moment, the expectation of x to the power of 1, which is equal to the it's equal to the first derivative. It's equal to the first derivative. So this prime is for the first derivative of the moment iterating function evaluated at t is equal to 0. Okay. So which means in order to find the mean, we need to take this moment iterating function, derive it once and evaluate it at 0. So we take this moment iterating function, derive it once. So you have e to the half t squared. So now the derivative of this moment iterating function, now you have the prime. So you want to use the chain rule. So you take we have e to the half t squared, and you want to derive e to the half t squared. So use the chain rule. You take the exponent, then you multiply by the exponent. So if you half t squared, then times e to the half t squared, then now you have to multiply by the derivative of the exponent. So derivative of half t squared is just gonna be t, because now we are deriving this with respect to t. So derivative of half t squared is just gonna give you t. Okay. Now, in order to find the mean, you just set the moment iterating function evaluated, the derivative evaluated at 0. So which means in the place of t we put 0. So I have half. Then instead of the t I put 0. So I have half squared times e to the half. In place of t I put 0. So I have 0 squared times another 0. So in the place of the t I put 0. So you find that this thing is equal to 0, which is the mean. Now this is a known result. Know that the mean of a standard normal is just equal to 0. So this is what I had here in the beginning of this video. Okay, now I want to show the variance because of the length of this video. So please like, comment, and subscribe and watch more videos.